Every year, over 5 million tons of structural steel are produced worldwide, enough to build more than 60 Golden Gate bridges. And here's the fascinating part. Almost all of this steel is born from scrap. Old cars, dismantled rail cars, and even decommissioned ships are given a second life. A skyscraper being built today could very well contain a piece of armor from World War II, and the most striking example of this transformation is the I-beam, seemingly simple yet capable of carrying the weight of an entire column of trucks. But how does a backbone of modern cities rise from piles of rusty metal? Stay until the end, because there's a hidden secret in this process rarely revealed to the public. The true genius of the I-beam lies in its shape. The flanges at the top and bottom carry the main bending loads, while the thin web in the middle connects them, holding everything in place. This clever design allows for incredible strength with far less weight. A single heavy I-beam, when installed correctly, can support hundreds of thousands, even millions of pounds. Imagine an entire row of fully loaded semi-trucks balanced on one piece of steel. That's real strength. The story begins not in a futuristic workshop, but in a chaotic scrapyard, a place that looks like a graveyard for metal giants. Mountains of old cars, broken railway wagons, twisted building frames, and industrial relics lie waiting. A giant crane swings overhead, its electromagnet crashing down and pulling up tons of rusted iron with a piercing screech. This scrap is the essential ingredient. It's loaded into an immense steel basket and sent into the furnace for a fiery rebirth. Steel holds the crown when it comes to recycling in the United States. The recycling rate for structural steel is a staggering 98%. That means almost every piece of steel from demolished buildings, dismantled bridges, and scrapped ships returns to service. On average, a new I-beam is made from 90% recycled metal, making steel one of the most sustainable building materials on Earth. Think about this. A modern skyscraper might contain steel that once rolled across America as a railway track in the 1930s, a car from the 1970s, and armor from a battleship of the Second World War. Each I-beam is not just a piece of metal, it's a living archive of human history, reforged for new service. Annually, U.S. factories alone produce over 5 million tons of structural steel, most of it I-beams. To put that in perspective, the steel in the Golden Gate Bridge weighs about 83,000 tons. That means every year, enough beams are produced to build more than 60 Golden Gate bridges. At the heart of steel production is the electric arc furnace. Imagine a cauldron the size of a small house. Scrap metal is dumped inside with a deafening roar. Then 3 enormous graphite electrodes are lowered, and with a surge of power, an electric arc leaps across them, an artificial lightning bolt striking the metal. The workshop explodes with light so blinding that workers must shield their eyes. Inside, temperatures soar to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It melts instantly into a glowing, boiling lake of liquid steel. Alloys and additives are introduced to fine-tune the steel's properties. The molten metal is then guided into a continuous casting machine. It flows into a water-cooled copper mold, where the outer surface solidifies into a shell while the inside remains molten. Slowly, an endless red-hot beam emerges. This bloom is cut into pieces, reheated, and sent into the rolling mill. Here, massive steel rollers squeeze the glowing bar with thousands of tons of pressure. Pass after pass, the shapeless bar stretches into a long ribbon, gradually forming the familiar eye-shaped profile. By the time it leaves the finishing rolls, the beam has near-perfect dimensions. It's still red-hot, so it glides onto a massive cooling table, hissing as it releases heat. Once cooled, it's straightened, cut, and inspected. Ultrasonic scanners probe deep into the steel, ensuring no hidden cracks. Each beam is stamped with its birth certificate, the steel grade, batch number and size, before cranes lift them into warehouses or onto trains. From there, they head to construction sites, ready to serve as the unshakable spine of skyscrapers and bridges. But steel isn't the only material that tells a story of strength. Titanium is another metal that reshapes industries. Every year the world produces over 10,000 tons of titanium discs, the building blocks for jet engines, surgical implants, and even spacecraft parts. A single disc can weigh more than a car, yet it resists both extreme heat and the vacuum of space. How does such a supermaterial emerge from a dull gray sponge-like mass? Titanium begins its life as ore, primarily ilmenite and rutile, mined from regions like Australia, South Africa, China, and Canada. The raw material is transformed into titanium sponge, a porous, brittle substance that hardly looks like the metal it will become. From there, the sponge undergoes a purification and heat treatment process to enhance its structure. Depending on the application, titanium is alloyed with aluminum and vanadium for strength and flexibility, or left pure for medical implants. Forging and casting shape the titanium into discs, which are then machined with incredible precision. Lathes, milling machines and grinders refine them until they meet exact specifications. Ultrasonic testing ensures no internal flaws, while polishing seals microscopic pores, making them resistant to corrosion. This is why titanium is trusted for aircraft engines and medical devices, where failure is not an option. And then there's copper. Every year, blast furnaces across the United States give birth to over 30 million tons of pig iron. To put that in perspective, that's enough metal to construct 250 Nimitz-class aircraft carriers, or more than 12 million cars. But this steel backbone of our modern world doesn't simply appear. It begins with what looks like ordinary reddish-brown stones, iron ore, that alongside coke and limestone are thrown into the fiery stomach of a blast furnace. Inside, under unimaginable heat, reaching up to 3,000 degrees, a transformation unfolds. Brittle rocks are turned into a blinding river of molten metal that will one day rise as skyscrapers, stretch across as bridges, and sail the seas as massive ships. The story begins far away, in quarries where miners dig up iron ore. It doesn't shine like metal yet. It looks more like rusty earth, because the iron inside is bound tightly to oxygen. The task ahead is to free the iron from this bond. To do this, two more essential companions join the process: coke and limestone. Coke, made from purified coal baked without air, is not just fuel, it's the thief that will rip oxygen away from the ore. Limestone, a simple common stone, plays the role of a cleaner, trapping unwanted impurities like sand and clay into a separate mass. All of these ingredients make their way to the plant where the true giant waits, the blast furnace. Imagine a tower, more than 100 feet tall, its insides lined with heat-resistant bricks, crisscrossed with pipes and platforms. This titan never sleeps, working non-stop, day and night for years at a time. Like a hungry stomach, it constantly needs to be fed. With a skip hoist, something like a rail car running up tracks, the iron ore, coke and limestone are carried to the top and dropped inside, layer by layer, like building an industrial lasagna. For every ton of pig iron produced, nearly 2 tons of raw material are consumed. What's left behind after the fiery process is concentrated metal, the true essence, stripped of nearly 700 kilograms of oxygen and other impurities. The real show, however, begins at the bottom. Here, special nozzles called tuer blast in air heated to 2,000 degrees Fahrenheit. The coke roars to life in an inferno, driving the furnace's core to nearly 3,000 degrees. At this level of heat, almost nothing on Earth can withstand it. As the materials slowly sink, they pass through different zones, each with its own chemistry. Rising carbon monoxide gas steals oxygen from the ore, leaving behind raw iron, while limestone gathers impurities into a molten byproduct known as slag. When the moment comes, molten slag flows out first, heading off to be cooled, and later used in road construction. But then the furnace reveals its treasure. A drill opens a tap hole, and with a roar, an eruption of blinding molten metal bursts forth. It isn't orange, it's white-hot, brighter than the sun to the naked eye. Sparks fly as the glowing river rushes into massive torpedo-shaped ladles, giant insulated containers on wheels, holding hundreds of tons of this liquid fire. This first product, pig iron, is brittle and heavy with carbon. It can't yet become the steel for our skyscrapers, or the cast iron for our frying pans without refinement. Some is taken to foundries, where additives transform it into cast iron goods. But most pig iron journeys onward, into oxygen converters or electric furnaces, where excess carbon is burned away, rebirthing it as strong, flexible steel, the true skeleton of our modern world. Just think of the scale. A single blast furnace in the US produces over 5 tons of pig iron every day, enough for about 12,000 cars annually. Across the country, only around 15 blast furnaces operate, just a handful of these titans, fueling an entire industrial nation. More than 90% of the pig iron they produce isn't even the end product. It's simply the first step, the raw foundation for steel that will become the towers of Manhattan, the bridges spanning mighty rivers, the cars driving down highways, the ships crossing oceans, and the very tools we hold in our hands. The story of fire and stone doesn't end here. From the fiery rivers of molten iron, industries have learned to create not just steel, but also byproducts that shape our daily lives. Take mineral wool for instance, a material known as the stone sweater for houses. Every year, the United States produces millions of tons of this insulation, valued at more than $4 billion, made from volcanic basalt and recycled slag from those same blast furnaces. It undergoes its own fiery rebirth in cupola furnaces. At 2,700 degrees, hotter than natural lava, basalt and slag melt and transform into golden threads, spun into fibers thinner than human hair. The result? A fluffy, fireproof, sound-absorbing material that keeps homes warm, quiet, and safe, an industrial cotton candy spun from stone, and the chain of industrial transformation doesn't stop there. Consider particle board, the backbone of modern furniture and construction. Over 108 million cubic meters are produced globally each year, recycling 16 million tons of wood waste. What was once discarded, shavings, sawdust, and even old furniture, now becomes sleek, durable boards. Through a process of chipping, drying, resin bonding, and hot pressing, the waste is pressed into three-layer sandwiches with smooth outer layers and a strong inner core. It's a material born from trash, reshaped into tables, shelves, and cabinets, a recycling revolution that saves forests and fuels sustainable design. From ore to steel, from slag to insulation, from wood waste to furniture, one truth emerges. Industry has mastered the art of transformation. Nothing is wasted, and everything can be reborn. Behind the fire, the roar and the blinding glow lies a story of human ingenuity, a relentless drive to shape the raw chaos of nature into the ordered skeleton of civilization. Each spark, each molten river, and each board or roll of insulation is not just material, it's a piece of the modern world, forged in fire, reborn through innovation, and destined to build the future. Inside the massive press, the wood chip mass is subjected to two unstoppable forces. First, enormous pressure, tens of kilograms per square centimeter, compresses the chips so tightly that not a single void remains between the particles. At the same time, the heated plates of the press, scorching at nearly 400 degrees Fahrenheit, transfer their heat deep into the mat. That heat sparks a chemical miracle. The resin begins an irreversible polymerization process. What was once a liquid glue instantly transforms into a rock-hard polymer, binding millions of wood particles into a single unified structure. Within minutes, a loose mat becomes a hot, solid, and completely monolithic particle board. But this transformation doesn't end here. Over 1 million marine creatures, along with countless birds and land animals, lose their lives each year because of plastic waste. What's most shocking is that the majority of this destruction comes from the things we casually use every single day, like the plastic bottle you might be holding right now. It may look simple, but the story behind how it's made and where it ends up is far more complex than most of us realize. The journey of a single plastic bottle begins deep underground, long before it ever reaches your hands. To create it, we drill for crude oil and natural gas, fossil resources that took millions of years to form. When ancient marine organisms and plants died, their remains sank into ocean beds or were buried beneath layers of soil and rock. Over unimaginable stretches of time, pressure and heat transformed that organic matter into the oil and gas we now extract to power our world and manufacture everyday items. But among all those items, plastic bottles remain one of the most common. To reach these fossil resources, towering drilling rigs are built, some rising as tall as a 30-story building. Offshore rigs push drill bits through layers of rock and sediment, sometimes thousands of feet deep, to tap hidden reservoirs of oil. Once crude oil and gas are pumped out, pipelines send them to refineries. Inside these massive facilities, oil is heated to over 600 degrees Fahrenheit in giant distillation towers. These columns, which can stretch 200 feet into the air, separate crude oil into its many components. One of those components is naphtha, a light hydrocarbon mixture and the essential building block of plastics. Although only about 4% of the world's crude oil is used for plastics, that small fraction has transformed modern life. From packaging and clothing fibers to electronics and medical equipment, plastics have become indispensable, and it all starts with naphtha. Naphtha undergoes a process called cracking, exposed to extreme heat, sometimes hotter than 1,400 degrees Fahrenheit. It breaks down into smaller molecules called monomers. Ethylene and propylene are among the most important of these, as they form the backbone